Okay, good afternoon. So today we are going to do our third week review, right? 115, 116 classical physics, 251 modern physics, which we call Intro to Relativity and Intro to Quantum Mechanics because that's the focus. And then you go on to 302 quantum mechanics, and 341, 361 classical mechanics and electrodynamics at the junior level. So today is 251 modern physics, or intro to relativity and quantum mechanics. And remember, the point of 251 really was about that in 1900, people thought they had solved all the physics, right? All physics was done. But there were a couple of cracks in the wall. There were a couple of problems that weren't solved. And the point of this class very much is about how those were developed, how those unanswered questions that were left around 1900 were studied and understood and developed to develop two whole new fields of physics and a whole new way of looking at things, and also a way of looking at things that says maybe we should never say we're done. And of course, it was very much precipitated by Einstein, but it definitely there were many more players, and his famous 1905 papers on Brownian motion, relativity, quantum mechanics, and I forget the fourth paper, but it involved one of those as well. Excuse me. So let's just start from the beginning. We left off in Physics 116, at the end of Physics 116, saying, Maxwell's equations. Maxwell's equations are about bringing together all of electricity and magnetism. Whoops. So it doesn't matter too much how much you know about Maxwell's equations at this point, or how much in depth we've gone into them in the past. There are four. Sorry, I don't know where I left off, but anyway, there are these four equations. Gauss's law we definitely know. Gauss's law for magnetism is basically the law that says there's no magnetic monopoles. Ampere's law with Maxwell's correction, that is Maxwell's correction. Ampere's law is about finding magnetic fields from collections of currents. Maxwell's correction is that there are magnetic fields even where there aren't currents. And Faraday's law, which is about generating electricity very much so. It's the fact that changing magnetic fields create electric fields, which therefore move charges, therefore create current. So when we put these four equations together, remember, it predicts light. But there was a problem. Somebody found, but certainly Einstein discussed the fact that Maxwell's equations don't predict that light speed will change when you change reference frames. So relativity is all about reference frames. So that's the first thing that we really discussed in 251 is relativity. Relativity is about reference frames. Relativity. Frames of reference, FOR. And Maxwell's equations don't predict that when you change reference frames into a moving reference frame, that the light speed changes. In other words, if light is coming at you at the speed of light, which we know of as 3 times 10 to the 8th meters per second, and you are in a stationary frame and light is coming at you at 3 times 10 to the 8th meters per second, but then you get into a car or you walk or you get into a spaceship that goes really fast, and you travel towards that light source, so that you would think that according to what's called a Galilean transformation, that the speed should just add, right? If a car is coming down the road at 55 miles an hour and you are standing still on the sidewalk, it travels relative to you at 55 miles an hour. But if you're on a bicycle going towards the car at 10 miles an hour, and it's traveling relative to the road at 10 miles an hour towards the car, and the car is traveling at 55 miles an hour relative to the road towards you, relative to the car, you're going 65 miles an hour, right? That's a Galilean transformation. So I just wrote the Galilean transformation in the corner here just to remind you that it just says that if there's two frames of reference, if one frame of reference is the stationary frame of reference, and that's your coordinate axis, your unprimed coordinate axis. That's your frame of reference. We call that O. And then you've got another frame of reference, O prime, which is moving in the positive x direction at a speed v. Then x prime, y prime, and z prime measured in the O prime frame of reference are transformed in the way shown. As long as the frame of reference is moving in the plus x direction, it's only transformed in the x direction, and y and z stay the same, and t doesn't transform. That was t equals t prime. This was a comma, sorry. And that means that velocities add, right? So if you, and the example I gave was that v is in the negative x direction, right? You're going towards each other. So that means that if a car is in this frame of reference and it's going at speed u, according to that frame, according to the primed frame, it's going u minus v. If the primed frame is going in the negative x direction, then it's going u plus v. That's right, velocities add. Of course they add. That's what we think. But what so that's Galilean transformation, you should understand that. What what Einstein realized about Maxwell's equations is that that doesn't work for light. If instead of a car in the unprimed frame, if that was a photon, which we haven't invented yet in 1900, and hopefully you know I was being facetious about invented, we haven't discovered the concept of a photon yet. All light was waves at that point. But we have, yeah, but anyway, if the car was a photon traveling at 3 times 10 to the 8th meters per second, which is the known speed of light in a vacuum, and you look at it from a different frame of reference, bizarrely, the light is still traveling at 3 times 10 to the 8th meters per second. So this does not work for light. No matter how fast you travel relative to the light source, it's still traveling 3 times 10 to the 8th meters per second relative to you. That's what Maxwell's equations predict, and the question is that true? So the first thing is we have, it's a hard thing to test because of the high speed of light. So the first thing we have is the Michelson-Morley experiment, right? The Michelson-Morley experiment is a test of this. And actually, you can review for yourself that the Michelson-Morley experiment is a test of, in order for this to be true, in order for there to be a Galilean transformation for light, the light has to have its own reference frame. And so Michelson and Morley are looking for the reference frame of light, looking for the ether, remember. And they couldn't find one. They couldn't find a difference in the speed of light in different directions relative to the source. So the Michelson-Morley experiment, there's no such thing as a measurement of zero, so they can't prove it, but they can put a lower bound on the fact that there doesn't seem to be an absolute reference frame for light, which means that light travels at 3 times 10 to the 8th meters per second relative to any frame, no matter how fast it's moving. Bizarre. So Einstein had to correct Newtonian mechanics to account for this. And that's where special and general relativity come in, special relativity in particular. And remember that in order for Einstein to come up with relativity, it's basically two postulates. He basically starts with two postulates and says, the additional information is Galilean relativity should be correct in most situations, except when except when things are traveling fast, but it should be a good approximation to reality, basically, Galilean transformation. So Einstein's postulates: 1, physics is the same in all reference frames. Physics laws must be same. Let me write this without you listening. So the laws of physics must be the same in all inertial frames of reference. These are the postulates, Einstein's postulates, that he comes up with special relativity from. Inertial frame of reference, remember, is what? It's one where the frame of reference is traveling at constant velocity. In other words, if you're stationary relative to, and let's just assume, right, yes, the Earth is not moving at constant velocity, but let's just ignore the motion of the Earth, and let's just take the lab frame as your stationary frame. If you're walking at constant velocity, then you're in an inertial frame. Laws of physics should work the same for you. If you're walking at constant velocity, if you're in a car traveling at constant velocity, if you're in an airplane traveling at constant velocity, relative to the lab stationary frame. In other words, laws of physics like Newton's laws and conservation laws. And simply, if you drop a ball straight down in an inertial reference frame, it should fall straight down, regardless of whether you're in the stationary frame or a moving frame. If you're in a moving train and it's traveling at constant velocity, you drop a ball, it's still going to fall straight down. The second postulate is the unusual one, which is that the speed of light is the same in all inertial frames of reference. It doesn't change. And then using the Galilean transformation, the ideas from the Galilean transformation is that motion we should still have a linear relationship between the position in one frame and the position in another frame. There should only be a one-to-one correspondence. In other words, if you have a position in one frame, it better not end up being two different positions could be viewed. It could be in two different positions in another frame. That just doesn't make any sense, right? That's hence why there's no quadratic terms in the new transformation. And so Einstein uses just those facts to come up with a new transformation, and comes up with, and maybe let's just say Einstein, the Lorentz transformation. The Lorentz transformation. And I say, well, so it's named after Lorentz, not after Einstein, because this concept had come up before. Transformation. So the Lorentz transformation is the new way to look at physics that leads to all the conclusions in special relativity.